Hey, we have here today a very interesting looking integral from the UNSW Integration Bee 2022. This was knockout round 2, problem 5. We have the integral from 1 to 2022 f of x dx. We have this definition over here to the right of f of x, that f of x is going to be equal to the floor of x, decimal place of x. Okay, now I think with a problem like this, especially with the floor function, this definition, it's really going to be all about just getting an understanding of what's happening, like just getting a feel for it. I like to kind of slow it down and like simplify it if I can in a case like this. So what I want to do to start actually is just to look at f of x and not worry about the integral yet, and we'll just look at some x values somewhere in this range. So like, let's start with an example. I'm going to look at f of 1.234, let's say. And we want to find a way to evaluate this to get this into a number value, and we have this definition. And so what they tell us to do is take the floor of x, where x is 1.234. So if I take the floor of 1.234, our x value, and then essentially the floor will round us down to the next highest integer. So in this case, it's going to be 1. So the floor of this is just going to be 1. That's pretty simple. So reading this out, they say take the floor of x and we get 1. So since we have a 1 here, we're saying we want the first decimal place of x. Well, the first decimal place of x is going to be just this right here. So this is going to be just this 2 right here. So for f of 1.234, we can evaluate this to 2. And then we could look at another example. Let's look at something like 1.0977. Well, again, the floor of this is going to be 1. It's telling us take the first decimal place. So this is going to return a 0. Then let's look at a different x value in this range. So let's say we have something like f is 3.782. Well, the floor of this value is actually just going to give me 3. It's going to round me down to 3. So that's saying take the third decimal place of x. Well, the third decimal place of x is going to be right here. It's going to be a 2. So we can say this expression is 2. So with this definition, we know that we can calculate the value of f of x anywhere, and that we know that our integral is just going to be a constant value that we can basically pull out. And so everything's just going to integrate to x. So this is actually pretty nice. So now that we understand f of x a little bit better, I think I want to look at our integral. And I still want to simplify this integral, and we have the floor, and often the way to use the floor is actually to still break this integral up into parts. Instead of looking at the whole integral from 1 to 2022, to simplify it a little bit, let's just look at it from 1 to 2 and see what happens. Okay, now what I've done over here to the right is just written down our function values for a whole bunch of different x values, but within our range from 1 to 2. And again, just to reiterate, in each case, we're just taking the first decimal place. Because everything starts with a 1, the floor takes us down to 1. So in each of these cases, we're just taking the first decimal place to get these values that you see over here on the right. And you'll just notice like 1.234 and 1.297, those are the same, they both give 2. Or like 1.555 and 1.507, they both give 5. So what that's telling me is I can break this integral down even further into the 10th decimal place, because we know for every 10th decimal place, we're going to have the same value. Okay, so now that I've broken up our integral into 10 different integrals, let's just evaluate each of these for our f of x value real quick. Okay, now first for this example, for the integral from 1.0 to 1.1, that's just like this case right here at f of 1.0913. We just evaluate to 0. And now that's going to be true for everything in that region. So everything here is going to be, we're integrating just 0. And so that part of it's going to go away because that whole integral is going to be 0. Then from 1.1 to 1.2, so for this integral, it's just like this case of f of 1.174, where it just evaluates to 1. So everything in this region here is going to be just like this one, and it's just going to evaluate to 1. And then our f of x in this region from 1.2 to 1.3, it's just like these cases right here. It's going to be something like 1.234. Our f of x value is going to become 2, and those are going to be all the same that way. And then last, like between 1.9 and 2, if we had something like f of 1.999, that's just going to evaluate to 9. And then we can just go ahead and integrate this thing, because again, we just have numbers here. So we're going to have 1 times x evaluated from 1.1 to 1.2, and then we're going to have 2x from 1.2 to 1.3, and this is going to go on, and we'll have our last one here of 9x from 1.9 to 2. Now, when we evaluate this, it's going to come up pretty nice, because like for x, we're going to have here 1.2 minus 1.1. Well, that's just 0.1. Then for this next one for x, when we have 1.3 minus 1.2, again, this is 0.1. Because the width of the region is the same in each of these is going to be 0.1. So we can just write this all out knowing that it's always evaluating to 0.1. But then we can just factor out this 0.1. But then this is just going to be the sum of numbers from 1 to 9, right? We'll just have 1 plus 2 plus 3 plus 4 all the way to 9. And of course, we could just add up these numbers, but there's a formula for the first n natural numbers, and it's just n times n plus 1 over 2. So our n in this case is 9, so this is going to be 9 times 10 divided by 2, or 45. So putting that back here, we're just going to have 0.1 times 45, or that's going to end up being just 4.5. So now that we have a value for our integral from just 1 to 2, we can do the same thing from 2 to 3. And we're just going to have to do this 2,022 times, and then we'll be done. Okay, hopefully we'll find a shortcut somewhere along the way, but let's just look at this next example. Okay, now for this integral from 2 to 3, it's very similar, but what I've done different here is instead of breaking it up by the first decimal place, I broke it up by the second decimal place. So instead of having 10 integrals, now we have 100 integrals, which of course I didn't write out. This is actually going to be, I did 2 rows, but this is actually going to be 10 rows right here. And the reason I did it, let's just look at some random f values. So if I have f of 2.734, let's say, and 2.734 is within our bounds of 2 to 3. Well, this now is saying take the floor of this, which is 2, and then take the second decimal place, which is this, which is just going to be 3. So that's why I need to break it up on the second decimal place, and that's how we get 100 integrals instead of 10. But now the interesting thing is when we evaluate this, it's going to work out very, very similar to what we just saw in the last example. Because let's just look at these 10. Let's look at the first 10, kind of the way we did the other ones. Well, again, this integral is going away. So again, when we integrate this, we're going to end up with like 1x plus 2x plus 3x. And the only difference is when we did this example, our x value was 0.1 in every case. But now the width of the integral is 0.01. So our x value is going to be 0.01. So for this sum now, what we can do is we can factor out, instead of factoring out a 0.1, we factor out a 0.01. But then this is still going to give me the sum of 1 plus 2 plus 3 all the way to 9. But we already know that that value is 45. And so when we multiply 45 times 0.01, now we get 0.45. So it's not that this integral here is going to be 0.45, as we have 10 of these. So now I need to multiply this by 10. And so that's going to give me 4.5 again. So the value for this integral is also going to be 4.5. So now from here, just to generalize what's happening, in each case, we're going to have that sum of 1 to 9, which is going to give us 45. But then we just multiplied this by the width of each integral, which was 0.1, and we just multiplied it by really 1 because we just had one row of integrals to evaluate. So when we multiply this together, we got 4.5. And then here, the same thing, we had 45, but then we multiplied it. The width of our intervals was 0.01, but then we had 10 rows, so we multiplied it by 10. But you notice what happens here is with 10 times 0.01, we always end up with 0.1, and this is going to continue that way because like for the next example, we're going to have our 45, the interval is going to become 0.001, but instead of having 10 sums to evaluate, now we're going to have 100, and so we still end up with 45 times 0.1. So what we find is every one of these integrals broken up this way all the way to 2022, they're all going to be 4.5. We're not going to have 2022 of these, we're going to have 2021 of these. We don't have this first one from 0 to 1, so we're just going to be evaluating 2021 of these times 4.5. And so you can just multiply this out, and what you're going to get is 9,094.5. Okay, so really, like I said originally, the whole problem was really just evaluating it. It was like understanding this original expression, really just getting this first value. After we were able to get this initial value of 4.5, at that point, we could pretty quickly jump to this step of just multiplying everything out. So we'll stop it there. Thanks everyone for watching today. Have a great day.